Myself, Maurya Satish. Roll number is 209-518-3329 from Computer Science and Information Technology Department. Subject is Theory of Computation. AIT, subject code is AIT C04. AIT concept video. Today we are going to discuss about the AAT concept, right linear and left linear grammar. First, we are going to discuss about introduction to regular grammar and its types, right linear regular grammar and examples, left linear regular grammar and examples, conversion of linear grammars. Introduction. Regular grammar is a type of grammar that describes the regular language A. Regular grammar is a mathematical object G which consists of 4 components. G is equal to n comma e comma p comma s, where n is non-empty finite set of non-terminal symbols, a set of a finite set of terminal symbols or an alphabet or symbols. P represents a set of regular grammar rules. Grammar rules, each of one having one forms. A tends to A comma B, A B, A tends to B, A tends to E. Here epsilon is equal to empty string. A comma B belongs to N, A belongs to N. Sigma. S belongs to N is start symbol. The regular language can be generated by regular grammar. In a regular grammar, the left hand side always consists of single non-terminal. The left hand side cannot have more than one non-terminal or any terminal variable. There can be a single terminal or a single terminal followed by non-terminal on the right hand side. Linear grammar. A linear grammar is a context-free grammar that has at most one non-terminal in a right hand side of each of its productions. A linear grammar is a language generated by some linear grammar. Let's discuss about types of linear grammar. Types of regular grammar. There are 2 types of regular grammar which are described as follows. Left linear grammar, LLG, right linear grammar, RLG. Right linear regular grammar. Right linear grammar means that non-terminal symbols will be at the right side of the production. It is a formal grammar. N comma epsilon comma n comma sigma comma p comma s, such that all the production rules in P are one of the following forms. L tends to A, where L is non-terminal and A is terminal in sigma. L tends to A comma M, where L and M are non-terminals in N and A is in sigma. L tends to sigma. M. Let us consider an example. Consider a language L is equal to B power N A B power M A, where N is greater than or equal to 2 and M is greater than or equal to 2. The production rules or grammar for the given language is L is equal to B power N A B power M A into B power M A, and or A is greater than or equal to 2 and B is greater than or equal to 2 is S tends to B comma B. For first 2 B's, B tends to B or AC. Any number of the B's followed by A. C tends to B D implies 2 B's. D tends to B D or A. Any number of B's followed by A. Let us consider more examples like A tends to A tends to A comma AB, and A tends to epsilon, where A and B are non-terminals. A is terminal and epsilon is empty string. S tends to 0 comma B or 1 S. B tends to 0 B or 1B or S or 0 or 1, where S and B are non-terminals and 0 and 1 are terminals. Left linear grammar. In left linear regular grammar, also called as left linear grammar, the rules are of the form are as given below. L tends to A, where L is non-terminal in L and A is a terminal in sigma. L tends to M comma A, MA, where L and M are in N and A is in sigma. N tends to epsilon, where epsilon is a empty string. Left linear grammar means that the non-terminal symbols will be at the left side. Example, consider a language B power n, A B power n, A, n or A is greater than or equal to 2, M is greater than or equal to 2. The left linear grammar that is generated based on the given language is S tends to B, A, last three symbols BBA, B tends to BB or DBBA for BM and BBA are the BN followed by A. D tends to BD, DB or E for B n minus 2. A tends to A tends to BA, A tends to epsilon, where A and B are non-terminals. A is terminal and epsilon is string. S tends to B00 or S11. B tends to B0 or B1 or 0 or 1, where S and B are non-terminals and 0 and 1 are terminals. Consider a regular grammar. Sigma is equal to A comma B. Initial state is Q naught A. Final state is F B. The right linear grammar corresponding to finite automata is A tends to B tends to epsilon by AB by BB. The above grammar is right linear grammar, which can be written directly through finite automata. Here given as A consists of B, where capital B is B, and in next A consists of AB, where capital B has both B's and epsilon, and we have another A where it contains both A, BB, and B consists of AB and B consists of epsilon. The above right linear grammar can derive strings that start with B, and after that any input symbol, that is sigma is equal to A comma B, can be accepted. The regular language corresponding to right linear grammar is L is equal to B, BA, BB, BAA, BAB, BBA, BBB, etc. Goes on. If we reverse the above production of the above right linear grammar, then we get A tends to BB, B tends to epsilon, BA, BB. It derives that the language that contains all the strings which end with B, that is L dash is equal to B, BB, AB, AAB, BAB, BABB, BBA, BBB, so on. So we can conclude that if we have a finite automata that represents language, and if we convert it into regular right linear grammar, which again represents language L, but after reversing right linear grammar, we get left linear grammar, which represents language L dash, that is reverse of L. Right linear grammar to left linear grammar conversion. The following steps will be used to when we convert the right linear grammar into left linear grammar for L. Step 1, for language L, we have to reverse the finite automata. Step 2, after that, we have to write the right linear grammar for it. Step 3, now we will reverse the right linear grammar. After step 3, we will get the grammar that generates the language which is able to represent the left linear grammar of the same language L. It can be shown in the diagram. Finite automata, reversing it, we get a finite automata when we write a right linear grammar, and when we reverse it, we will get left linear grammar. This represents the same procedure as above for converting to right linear grammar to left linear grammar. Here L is used to describe the language for finite automata, and LR is used to describe the reversal of language L. Example, in this example, we will use the above finite automata representing language L and accept all the string that begins with symbol Y. This language contains input symbol, that is sigma is equal to x comma y. Here we will convert this automata into left linear grammar. Solution. The reversal of finite automata described as follows. Step 2. For this reversal, a finite automata, the corresponding right linear grammar is described as follows. First one, x tends to x comma y or yy or yx. x tends to epsilon. Step 3. Now we will reverse the above right linear grammar and get the following grammar. Y tends to x, yx or yy or xy and x tends to epsilon. So this grammar is left linear grammar which is used to represent all the string that begins with the symbol y. So L is equal to y, comma yx, yy, yxx, yxy, yx, yyyy, etc. Left linear grammar to like right linear grammar conversion. To explain this, we will take the above grammar which is used to represent the language L and accept all the sets of string that begin with variable y. The left linear grammar for the above grammar is described as follows. B tends to BA, BB, AB, A extends to epsilon. Step 1. In this step, we will convert a left linear grammar into finite automata. This is the same process of conversion as described above. So, reverse the finite automata. Initial state is converted into final state and convert final state to initial state and reverse all edges. Reverse the finite automata. Initial state is converted into final state and convert the final state into initial state and reverse all edges. Step 3. Write right linear grammar corresponding to reversal. Reverse the finite automata. A tends to BB, B tends to AB or BA, BB or epsilon. Regular grammar is given rise to regular language, which gives rise to finite automata, which always gives rise to regular grammar. This is a cycle. All have the same power and can be converted to other. Thank you.